enjoy over a 4 days international conference. And of course, you can interact very here. All the participants here are ready to help you.
Of this historic section, especially to our co-organizer, Mahatma Gandhi University, India, Wuhan University, China, and our respective parties involved. We are having an international 4-day webinar on nanotechnology, biofabrication, and polymer. During this session, we will be sharing, liberating new technologies and the best practices. We are having an international 4-day webinar on nanotechnology, biofabrication, and polymer. Within this session, we will be sharing, deliberating the new technologies and the best practices by various presenters across the world. Ladies and gentlemen, we are delighted to welcome Professor Kaushik from Wuhan, China, who was pleased to be with us in this webinar. Respectful Professor Kaushik, I must thank you personally for taking off time from your busy schedule and be with us. And we know you represent a rare breed of person with brains and complemented a lot of muscle power, and I'm sure you can add a lot of value in your idea towards activity and serpent's development. We are always be very grateful on your contribution in connecting us with the key personalities in organizing this webinar. We are also honored with your assistance in the area of competency development among all our staff and students. We need to expand from institutional level to the international level. I'm sure a lot of our people among the audience today in this webinar are involved in competency development in their institutional capacity. We need to go beyond in contributing to the capacity development of the country. As a nation, we need to prosper and proud about the hidden potential of our staff. I am very happy that we have such a caliber person who are actively involved in such a magnitude, especially in the field of polymer and material science application. And I welcome the presence of Professor Sabu Thomas from Mahatma Gandhi University, India at this conference. May I also take this opportunity to recognize my team, especially Director Madam Rosnoiza Abdul Majid and her committee who worked very hard to make this conference a great success, and also the dynamic staff of IKTN So there are speakers from local universities, i.e. University Malaya, University Tun Hussein On, University Technical Malaysia, Malacca. Nevertheless, there are also speakers from India, Bangladesh, Jordan, Portugal, United Kingdom, United States, France, Turkey, Russia, Argentina, Mexico, Japan, Greece, Jordan, Canada, Slovenia, Ireland, and Brazil. And also all the people who are interested in science and technology development who have gathered virtually today. So let's enjoy, let's enrich, let's expand, and let's excel in the field of science and nanotechnology. Finally, I sincerely wish all of you a very productive conference that will support the safe, integrated, and responsible development of nanotechnologies. More specifically, it is my hope that you will not only be able to advance our thinking through the lively exchange of information and the significant brainstorming that should take place, but also to develop consensus positions on some of the key issues that characterize the different fields of application of material science, nanotechnology, and biomanufacturing. I am sure it will be a memorable experience to all of us. So let's enjoy, excel, and get the best out of the conference. May I wish all of you good luck and the very best. Thank you.
Thank you of the video of Muhammad Iqbal bin Muhammad Noor. Our first presenter for this morning is Professor Dr. Sabu Thomas from Mahatma Gandhi University. They give introduction and present about his topic, New Opportunities in Sustainable Nanomaterials. I would like to invite Prof. Kaushik to share his session.
I would like to I would just like to announce Professor Sabu Thomas sir, please uh, join us. Uh, is it audible?
Yes, sir. Can. Continue.
Okay. Okay. Actually, yeah. So you can please start your the enthusiastic words for our young students, scholars, and faculty members, as well as because you are a great inspiration for all of us to make more achievements in research as well as in academic career. So I would like to welcoming you. Please say something about our future, how we'll achieve, and then you can start your um, enthusiastic lecture. Please, sir.
Yeah, I think it's some networking issue. He will join shortly.
From Wuhan University. Nagaran is a very good friend of mine. He visited my university a few years back for a international conference.
Yes, sir.
We are still in touch. And all my academic friends, participants from 19 countries. I'm really excited to know that. And dear students, congratulations to all of you for organizing such a wonderful international conference on material science, nanoscience, and biomanufacturing. Excellent title. ISC Yemen 2021. I am glad that my university, Mahatma Gandhi University, is a partner for this conference with IKTBN. And Wuhan University, represented by Professor Pai, is also a partner. Let me congratulate Professor Pai and Ms. Dinagaran organizing this wonderful meeting. Conference and meetings are extremely important for students in academics. If you look at my university, I organize at least 6, 7 conferences, international conferences every year. Some of my meetings are in cooperation with the Professor Pai. Since we organize a large number of meetings, my students, my faculty members are able to connect with large. Covering the world, I am I remember my advisor, my collaborator, advisor from Canada, to my work for about 15 years. Always was for the ACS meetings. Told me, once you get an ACS meeting, you are completed. You will be exercising. So, renowned professor of political science, this is what he told me. You go to an ACS meeting, you are very active, participate in the meeting, you understand the leadership. It's a very important point to do. You listen to diversity, you listen to experts, and you understand the latest development. I request my students and friends interact with the speakers, understand the subject, try to collaborate into very good information. Trace the history of mankind. Historians used to classify the early ages of man into the five materials levels. So we have storage, people who make this store property. We have iron, bronze. We are on the age of politics, the age of longevity, the age of management. Glad that there is all and we are exposed now. All the best of the country. So conference, you must come out with a document, and that will be very important. And that document could be published in national journals. So Paul is very active. After the conference, you should think of publishing a book, publishing a special issue in leading journals. Therefore, participants will have lots of opportunity to publish their research. And I'm very pleased to see the facilities for material characterization. I could see your transmission electron microscope, SEM. I could see your magnetometer. I could see your differential scanning calorimeter, a range of machines I could see. I could see the way you collaborate with companies. That is extremely important. My university is also cooperating with a large number of companies. Collaborate with them. That will give lots of ideas for the young students. Therefore, I wish all the best for this wonderful meeting. And I wish a very, very vibrant meeting. Good success for the ICS MNB 2021. Thank you so much. And let us host many such conferences in the coming years. Join me. Thank you. And my university is very happy to interact with your institute, and we can have MOU, we can have several programs like exchange of students, faculty members, exchange of facilities, undertaking new projects. I have ambitious program of working together with your institute. Thank you so much, and I wish you all the best in the world. Can you see my slide?
Yeah, it's visible, sir.
Nagaran, can you see my slide?
Yes, sir, visible, visible.
Is the slide moving now?
Yeah, yeah, it's moving.
The slide moving now?
Yes, yes, sir.
Perfect. So I'm going to show you my first slide. The title of my lecture is New Opportunities So you will see all aspects of this in my lecture. You will see a lot of biomanufacturing. And I represent Mahatma Gandhi University right now, the Vice Chancellor of the University. And this is the emblem of our university. You can see the spinning machine, the hand-to-hand spinning machine used by Mahatma Gandhi to teach us self-reliance, the fight against the British, the technical and stuff. And this is my website. If you're interested to know more about my group, these are ACS data. It is 1.6 billion tons of agro waste is produced globally. In my talk, I'm going to tell you what can you transfer this agro waste into bio. That is the essence of my talk. Most of the bio waste being accumulated in different parts of the world are not utilized, they're underutilized. If you look at the agro waste, can you see my agro waste slide? The slides are moving. Can you get the slides are moving?
Yes, yes, sir. Yes, sir. Support
Yeah. If you look at the agro waste, we have sugarcane, seed, brine, rice brine, variety of. And I'm glad that in Canadian University, he talked about how plant fibers utilize to manufacture their powders. And look at the worldwide production. You will find that wood is number one. If the wood production is number one, we get from the stem, worldwide boundary, ultimate, fuel, and now, flags. We have a range of natural products. And they're not utilized. And many of these natural fibers are being wasted. In Kerala, we have a taste of food plantation. After the pineapple is harvested, these fibers are being wasted. Similarly, banana. After getting banana fruit, the stem is being wasted, not utilized. Of course, there are uses for other fibers like oil, jute, etc. Several vegetables. Look at the features of these environmentally benign and environmentally friendly materials. They're cost effective, they're abundant, they're durable, they're non-abrasive, they're very eco-friendly. and they provide lots of employment opportunities. Now my university is starting a production of fiber from pineapple. We have installed a couple of machines. When you visit my university each time, you can see how fibers from pineapple stem, pineapple tree, similarly banana stem. This slide will show you the different types of fibers. House fibers, that from the stem, the example is jute. Leaf fiber, the example is pineapple fiber or sun fiber. The fiber that you get from the seed fruit, a good example is coir. I think Malaysia also has a lot of coir, coconut trees. Grass fibers, palm fiber, also grass. Look at the banana plants in Kerala. There are a variety of banana plants. I know oil palm is one of the big industries in Malaysia. And we have lots of projects with oil palm. I work with several Malaysian colleagues to make advanced functional materials for oil palm. It's a very big industry in Malaysia. We are also working in the production. And look at pineapple, it's a big industry in Kerala, big plantation in Kerala. Fire. We get beautiful things from fire. We can make variety of articles out of fire. So we are working in the production of fire. Looking up to show you the price of this. If you look at the range of why is taking index of rare. You is a fire for cheap, for flower. They only panic shots. It has strength and modulus geometry. In the range of 1.51, much lower than glass. So if you take the specific properties, tensile strength divided by tensile, plus divided by tensile, it can be glass fibers. That's the beauty of it. What's the chemistry of this material? The main component is cellulose. We are fantastic philosophy, so the chemist can make wonders. This is a fantastic molecule where you can do a lot of chemistry. Look at the next component, lignin. We are making nanolithium. We are making lignin-based composite material. Lignin is also a very exciting material. These are the main components of it. Let me show you another important thing. The hierarchical structure of mathematics. The hierarchical structure of mathematics. What does it mean? I remember when I started in Mahatma Gandhi University in 1987 as a lecturer, I used to wonder a lot on this. Just chop the fiber, make I have several plans. Then we started making microfiber. They're all microfiber. And now we focus on nano. So we are able to work in three hierarchical length scale. Macro length scale, micro length scale, it's okay. Let me tell you why nanometer. It's a strategic platform. The most important nanomaterial, as a good say, really matters. I watch very high mechanical strength. Density is low. As a result, the species property is very good. Therefore, There is every need that we must utilize here for making value-added advanced. Let me show you the photograph of nanocellulose. If you examine the electron microscope, nanocellulose looks like sort of web-like interconnected structures. Look at the diameter of this will be the 20 and it's long. Probably can measure the length. One can bring chair out of it. Oh, measure the length. Steam explosion was something all stuff in the air, under a high pressure and temperature. What is happening? You have a policy. This is the raw everything to the then some will be the pressure and this explosion. And they structure what you remove the show you a slide. You do find out the whole thing. Now, you go from algae and we use a mild acid, you get low. So you can get cheaper. B29. Second one is nanofiber, long nanofiber, range of several micrometers long, several micrometers. Let me show you the facility at MGU campus. Look at what we have developed in the MGU campus. This is the raw fiber that collect from the agricultural waste, agricultural land. My PhD students collected, of them and put into the steam explosion unit, go for a bleaching, acid hydrolysis, repeat the process sometimes for 3 or 4 times to get the nanomaterial. This is what we have in the laboratory. Let me also show you the dynamics of the enrichment process. If you look at the raw fiber that we get from the plantation, cellulose content is 64, banana, heavy cellulose 18, lignin is 4, then you have other things. You have waxy materials. But when you do the steam explosion, hydrolysis, you look at you can't use the amount of remove, progressively remove these. Let me show you some nice pictures we have made. Why is it been published already? Look at banana stalk. From banana stalk. PhD student of mine is now in the US looking for what we have beautiful nanostructures. Something we have made from wood flour in cooperation with the Swedish Institute. In India, a student of mine went there. He made beautiful nanostructures from wood flour, a fermentation. We did enormous work on apple leaf fiber in cooperation with the South Florida University in Brazil. Look at the structures we have. Banana leaf, sorry, pineapple leaf. Let me show you another important slide about interface modification. Probably you all know that nanocellulose is highly hydrophobic because of the. This is a nanocellular structure. Dear friends, we can do wonderful chemistry of the surface. We can do acidification reaction. We can do both the OH will be converted to CO, OH. You can put fluorescent labeling and you can do wonderful spectroscopy work. You can do polymer grafting. You can do cellulation reaction, make it hydrophobic. You can do fraternization reaction. So right now I've signed a contract with Apollo Tires, India, the biggest manufacturing unit of tire, to do cellulation. Nanocellulose for inner lines. Let me now show you some of our recent work. How nanocellulose could be utilized for water purification. How we can use it for EMI sheeting. How we can use it for own healing. How we can use it for sensors. Let us take water purification. You know, water is going to be a very, very important material. And UN says that within 10 years, water is going to be a very scarce material, especially clean water. There is every need to design cheap material for water. I will show you our strategy to make filter membrane. See, if you look at a typical filter for water purification, they're all made of bilates. The bottom non-woven microfibers. The top one is what we have done is filter becomes very efficient. The filter becomes very efficient to remove dyes, remove suspended nanoparticles, heavy metals, oils, bacteria, and virus. Let me show you how we have removed crystal violet dye. See, green dye, giving beautiful colors. And you know what do they do? The textile industry, after the manufacturing process, they pump out everything into river water. It's very important that we must remove this dye. And see what protocol we have done. We have made nanocellulose made up. Nanocellulose very simple in chemistry we have done. If you do that, look at these very efficient. The absorption capacity of the dye. You show them that if you chemically modify nanocellulose, you get wonderful separation, you get wonderful separation coefficients. How do we do that? Look at this. This is our membrane. You can see most of the crystal violet dye particles have been moved. They are reaching the crux of the membrane. You might ask how it is being done. There is electrostatic interaction between modified nanocellulose and crystal violet dye. Look at the electrostatic interaction. It is a core reason for high efficiency separation when you do a surface coating with nanocellulose. Let me show you another important slide. You can also remove suspended particle. Water is increasingly contaminated with suspended particle. We all know that. So Gopakumar and I, with the Brazilian partner, we try to separate several types of suspended particles. Look at the art if you do into water. And then try to separate them. Look at this impure water. It's black in color, full of Fe2O. And this is after filtration. You see the filtrate is completely free from all this suspended particle. If you look at the feed is not able to transmit any light because a lot of countries you have suspended particle. After filtration, look at this. Look at the bottom part of the filter. All this suspended particle. These are retained by the filter in the top. Filter. Electrospan are able to remove suspended. What they've done, the film and glow, the first order of this paper is found. What they did is they did a very interesting work. They made nanocellulose aerogel, at least 1%. And then what they did is they modified the surface of the next slide. See? They gave a titanium dioxide coating on the surface to make it hydrophobic. And then what they did is, look at, they poured into, they put everything into seawater. decided to hold it. You sprinkle this in the seawater. You know, seawater is increasingly contaminated now with oil. Very often you read in the paper that uh, the ship, uh, the oil is getting into the water. There could be leakage in the shore of the ship. This is an excellent way of trying seawater. You can also remove metallic energy. Probably you all know that. Even in Malaysia, I know water is contaminated. You know, there's some parts of Malaysia. Not just in part of India, we have big contamination problem with water. Chromium, CNQ, copper, lead, etc. Look at the separation efficiency with the nanofilm. You can remove chromium, chromium 6, electropositive. 6 is electronegative, so you can have electrostatic reaction. They can remove chromium. Look at the equilibrium absorption of chromium. Similarly, look at the next slide. You can remove nickel. You can remove cadmium. You can remove lead. And I have a comparison here. You can also use, you know, in the olden days, people use rice straw fiber to remove metal. This is a village technology. And there's a comparison, rice straw fiber, normal microcellulose, this is nanocellulose. So dear friends, you're able to remove nickel, cadmium, lead, chromium. The thing is, we brilliantly use this base powders. This can do something interesting. Nanocellulose is able to kill coronavirus. Nanocellulose is able to remove bacterial life. I'll show you one slide. If you cellulose with polyamine, you can put a lot of amine groups on the surface, making nanocellulose electropositive. You all know that all the viruses, including coronavirus, has a negative charge on the surface. And nanocellulose can interact with this coronavirus and with DNA. Therefore, my friends, with bacteria, we can remove viruses. Bacteria is removed by size exclusion because size of bacteria is bigger. We can remove by size exclusion process. Look at a beautiful photograph. A gentleman's figure of burnt in his face, and his face is covered with nanocellulose gel. And within a couple of days, the cellulose is so fine as nanocellulose is so much. It is a very good deal for making solution. Look at the heart. Enormous. We have finally what we have made, the Brazilian collaborator. We have made nanocellulose, polyurethane. This is something very interesting. We have a series of applications. This material could be utilized for wound healing, sustained release of antibiotic. I can show you very interesting work where people have made nanocellulose yogurt. An antibiotic is incorporated into this area. And you can see beautiful sustained release of antibiotic. So dear friends, this is a very sustainable platform. form. Interesting slide from Professor Liu of China. Professor Liu of China, what he has done, he combined nanosecond nanocellulose fiber collide 0.0 to 0.0. Look at the Blue suggested that it's an excellent material for biological wound dressing. Combined nanocellulose and collagen. Nanocellulose has one more important application, especially to reinforce commercial filters. Commercial filters that you get in the market for water, they all have weak mechanical properties. For example, let us take polyacrylonitrile electrospun membrane. Look at the strength of steel. Very strength is very weak. If you give coating on one side of this membrane, strength increases. If you give coating the nanocellular on both sides, it comes around. Therefore, commercial filters could be made stronger by coating with nanocellulose. Let me show you another important slide, what they have done during the pandemic time. He submitted a major Indo-US making a new mask. Look at this slide, our mask, new mask. Of the almost outer layer in the centripetal coronavirus. If at all some virus is getting into your mask, this middle layer is possibly cheap. And the innermost layer is the most comfortable. So this is a big program we started with the National Science Foundation. You can see our design of our mask. This is the coating, this is electrospun nylon, this is our we also propose that it will be 3D printed. Let me now show you some of our work on sensors. This is a very interesting one. Look at nanocellulose and CND together. See, this is nanocellulose and CND together. You mix nanocellulose and CND together, and you mix with rubber latex. Malaysia has a lot of rubber latex. Once upon a time, Malaysia was #1 in natural production. Now you are #1 in oil palm. I think Thailand has a lot of them. Followed by mixing, coagulation, hot pressing, you make a fantastic composite of natural rubber with CNT and nanocellulose. What's the purpose of this? Look at this slide, very interesting slide. If you take nanocellulose, keep it for 25 minutes. How do you hybridize nanocellulose and So, dear friends, if you hybridize with carbon nanotube or graphene, you can make fantastic structures. Look at the dispersion. Dispersion is excellent when you hybridize CND and nanocellulose together in natural world. We don't hybridize all the CND agglomerates. I'm going to show you one slide because of lack of time. I must try to show you. If you make a nanocomposite of natural rubber with CNT and you measure conductivity as a function of CND volume pattern, you see you have a beautiful percolation. But if you mix CND and CNC together, fine if you put natural rubber, look at you get percolation at 1.5 with fraction of the combination. The mechanical properties are excellent for the combination. So there's lots of advantages mixing nanocellulose and CND. Look at this is nanocellulose and graphene oxide. You have the similar situation. Look at if you take graphene oxide alone, you have to add something like 1% or 0.85% of graphene oxide. This is what fraction. And if you use a combined thing, that the population is this is for a lot of applications making sense. Let me show you. We are also into neurothings. We are also into making batteries for lithium electrodes. We are also into making paper electronics. We are also into making capacity. Let me show you some stuff. I want to show you the work of Professor Man. He made aerogel and he went for pyrolysis. He made nanocellulose armor. They make nanocellulose, make aerogel, use aerogel. When you carbonize it, we hydrogen and make a then it could be an excellent anode material for lithium ion batteries. Use it as porous. Electrolyte, conductor, electrolyte, electrolyte. So we can have very efficient lithium ion batteries. Let me show you something we have done in my laboratory with my PhD. Ibuprofen made nanocellulose. Then he put an amine into it. For in situ polymerization process. And then, see, this is the total process. We made nanocellulose paper in my laboratory. We have in situ polymerization of nanocellulose and amine, or for a vacuum filtration or pressing, we made in conductive flexible nanocellulose. What is the use of this? It's an exciting material for mobile phone EMI sheet. Very flexible EMI sheetless we have made. This is very conductive. And this is very important for shielding application. Look at the shielding form we got. We got 23.
Hi everybody, my name is Ken and I'm the director of Angkasa Quarries Plastic Sandaran Part. Our company is a recycling company and we have started up the company around 4 years ago. But prior to that, I have 25 years of experience in the area of plastic recycling. Right now, our company main processing is doing recycling of plastic waste. The company, which is short form, the acronym is ANCOP, Angkasa Quarries Plastic Sandaran Berhad. We have full compliance from the government, from the ISO 14001. We have a compliance in the Department of Environment. We have compliance with the municipal government bodies of Malaysian government. Our main job is not only to make money, but obviously it's part of it, but then it's also to help the country to develop to a state where we are able to bring in processed waste material to reduce the waste that is dumped in the country and help out with whatever we can do. Even in the area of landfill, we are extracting plastic waste, we convert it into usable plastic. We hope that this program will work well. At the same time, what we have been doing is work with the various colleges and universities in Malaysia to bring them the knowledge and equip them with a better knowledge of recycling. And in time to come, we hope in the next few years with this program and the courses run by our company, students will be well trained and be more cautious about our environment. We hope that the government of Malaysia will continue to support us on the long term, and the staff in ANCOP, they are all very hardworking, and we feel that we still have a long way to go to achieve our goal. We appreciate that whoever that is looking into this video, and if there's any need, you want to talk to me, you can by all means get in touch with me. Principally, we are just doing recycle. Our main product is LDP, HDPE, PEPA, ABS, mostly all the plastics that you can mention. Even PET we are doing in a large scale. So anybody who needs help, we are very glad and happy to help you all, to assist in whatever setup you all need. Thank you very much.
Thank you, Prof. Ungkeng Sigmund, for wonderful presentation. We move on to the next presenter, Dr. Madhu Mohan from Banari Aman Institute of Technology, India, to speak about hydrogen bond thermotropic liquid crystal, optical and electrical application. I would like to invite Mr. Hamdan to chair this session. Thank you.
Right? Yeah. Hello. So now I would like to invite the movement from Analytic Documentary India. We talk about emerging bomb, thermography system, the analytical application. So, okay. So, make the move.
Can you see my presentation?
Yes, sir.
Can you see my presentation?
No, sir.
No, I'll share.
Yes,
Is it visible now?
yeah, yeah. Now, I think, yes, yes.
Oh, thank you. So I'm Dr. Madhu Mohan, talking from Banariaman Institute of Technology. I'm from India, and I'll be talking about hydrogen bond thermotropic liquid crystals, their optical and electrical applications. So this is my abstract. I'll be talking about the liquid crystals, which are rod shaped, and I'm working in hydrogen bonded liquid crystals. So we talk about some of the phases which are extensively used for thermal, optical, and electrical applications. I talk about the optical shutters, modulators. Then I'll be talking about the shuttering action, and then I'll be going to the memory devices where these systems can be used for memory. In fact, there are two types of memory, the optical and the electrical memory. And lastly, I'll talk about the thermistor. You can derive thermistor from liquid crystals. That is what I'll be talking about. Now, first I want to show you the formation of liquid crystal. Please view this book. You see, I had heated the liquid crystal and kept it on a glass slide where you have grooves. And once it is cool, you can see the formation of the liquid crystals. Is this movie visible? Is it visible?
Yes, sir.
Okay. See, so this is what you see. You can see the liquid crystal which is flowing in the grooves. At the end of it, it will form a crystal. This is what we call a liquid crystal. So this is how, in fact, the formation of the liquid crystal. So at the earlier stage, when we just heat it, you can see here, it is only a liquid flowing in the grooves. And as we cool it, you can see the liquid crystal. So this is what how a liquid crystal is seen under a polarizing microscope. Now I'll go to the next slide, next book, where I can show you what is switching, electrical switching. So here you can see the bright and dark. When you give electrical impulse to a liquid crystal, the liquid crystal will switch. What is switching? You can see this is dark now. When it is given opposite polarity, it becomes bright. This is a fundamental, important characteristics of a liquid crystal. Only some phases, like metric C phase, does this. If your liquid crystal is switching with respect to an AC voltage, then it can be used for devices. So this is what we talk about. Then I want to show you one more movie where the thermally controlled optical shutter we made. You can see, now you can see the liquid crystal here. This is opaque. Now I'm trying to heat the liquid crystal. Now the liquid crystal is being heated on a heating pan. This is iron box in fact. Once this is heated, you can see here, it becomes transparent. So this is what we call a thermal shutter. I show it here again. You see, this is opaque, and now as I heat, it becomes transparent. So this is what we call a thermally controlled optical shutter. So if you do a heat pulse, it becomes transparent, and at the lower temperature, it becomes opaque. So this is what I want to do. Now I want to talk about the optical shutters and modulators. It is an optical shutter. Where do we use it? Optical shutters, shuttering, if you take a camera, we want to use the shutters. In the initial days, they used to use the mechanical shutters. And later on, they moved to electronic shutters. Now, what is the difference between a mechanical and optical electronic shutter? Electronic shutter, the shutting time is in milliseconds. But in mechanical, it cannot be in milliseconds. So here we made optical shutters using liquid crystal. Now I talk about modulators. What is light modulator? Modulator is something which changes the color of the sample. So this is what here we show. This is what we call a liquid crystal texture. Once I heat it, this is a thermally controlled shutter. It becomes opaque. You can see here dark. And we can see here, I can show it here. This is the texture. And as I start heating it, it becomes opaque. This is what we see here. You can see this is what we call levotartaric acid. This is the chemical structure of it. This is what we call a levotartaric acid. And it is a ferroelectric material. And when you use these hydrogen bonded levotartaric acid, alkoxybenzoic acid, liquid crystal, when you start heating, it becomes, it can be used as a shutter. I can show you another example. You can see here, this is hydroquinone and a liquid crystal. That is alkoxybenzoic acid, you can see, and this is the hydroquinone. And you can see here, this is a beautiful shutter. This is not with thermal field, this is with electric field. As I go on increasing the electric field, you can see the shuttering action. Here, you see plate 1, plate 2, plate 3, plate 4. And as I go on increasing the electric field, the electric impulse, this becomes opaque, and this can be used elegantly as an optical shutter. I can show you one more example here. This is chlorobenzoic acid. You can see here, this is hydrogen bonded with chlorobenzoic acid. And you can see this is the conducting area, this is the non-conducting area. So when we started giving voltage, you can see the difference between conducting and non-conducting. See here, this part, which is the conducting part, becomes opaque, and the other part remains as it is. So this is only to demonstrate that thermal shutters, you can get thermal shutters using electric field, because previously I have shown with thermal field. This is with electric field. You can see here, we have given a field of 10 volts per micron. And then when we increased the field, you can see the variation. This is 0 volts, this is 4 volts. And as I increase to 4.0 volts, you can see the optical shuttering action. So this is what we call the shuttering action. Then going ahead, I can show you a few more examples of optical shutters. Here, this is a succinic acid. This is a succinic acid molecular structure. And this is what we call the nematic phase. You can see the threads inside it. And once you apply the phase, this is what we call the light modulation. You can see here it is blue and it is changing the color. It's not optically shuttering. It is not shuttering the light, but it is changing the color. This change of color is referred as modulation, optical modulation. You can see a variety of optical modulators. That is, you have a nematic phase and then it is shuttering here. This is what we call the optical shuttering. And here you have a blue phase, which is the spectric C, broken focal conic. And when you increase the field, it becomes light modulator. So here you can see both the optical shutter and the light modulator. This is typically a sample which we can show both of them. And going ahead, I can show you another optical shutter. See here, this is the bright texture of the chlorobenzoic acid complex. And when we are given electric field, you see it becomes optical extinction. That is a dark shade. That is, it is not allowing the light to pass through it. So this is a typical. This is the conducting area, and entire is conducting area. I just I've shown you how it behaves with field and without field. So this is with field, where you can see the shuttering action, and without field you can see. And going here, we have multiple cases of what we call optical shuttering here. You can see the clear optical shuttering. This is benzoic acids. And these optical shutters are extensively used because what is the advantage of these optical shutters? The advantage of these optical shutters is that the shuttering action is in milliseconds. So if you give a field, a desired field, the shuttering action happens within no time. It happens in milliseconds, instead of -3 seconds. And here, now we have seen, this is again another sample where the optical action takes place. I have calculated the, I want to characterize it not just by light, but by dielectrics also. So we have taken the permittivity. How is the permittivity with respect to the applied voltage? So when we increase the voltage, the permittivity increases. Here, in fact, the optical shuttering action happens. You can see the optical shuttering. And when we decrease the field, again, the light is allowed to pass through. And this is what we call a characterization through dielectrics to demonstrate the optical shuttering. And I can show you one more, the same thing. This is the capacitance, that is the permittivity, and you can see the same effect. So this is beyond doubt that it is happening. Now we tried it with multi-volt carbon nanotubes. So what we did was we dispersed multi-volt carbon nanotubes. So we have taken the liquid crystal, and in that liquid crystal matrix, we have used sonator, and we have dispersed the multi-volt carbon nanotube into this matrix. Once it is done, you can see the optical exchange at a very low voltage compared to the non-MWC. So we have given one modeling for it, why it is happening. So this is the liquid crystal moiety, and these are the MWCNTs. And once you give the field to this mixture of MWCNT and liquid crystal, the orientation of MWCNT with respect to the field is very fast. That is forcing the liquid crystal resurgence to align with it. You can see it here. So here we have all the things here. This is the glass substrate. This is the liquid crystal. 2 is the liquid crystal. And 3 is the MWCNT, these cylindrical substances. And E, this is the direction of the electric field. And once we give this what we call optical shuttering action with respect to MWCNT is happening. And I can show you the same way. This is now we have done with without what we call the MWCNT. So this is a beautiful texture, and this is the extinction. So we have calculated this through the dielectrics. So also you can see with the optical shuttering, there the permittivity is at its zenith. Then there is light passing through it, and then there is you can characterize it through the dielectrics also. Now we have given a modeling for this. What is that modeling? So this is what we call the polarizer. This is analyzer, because a liquid crystal is tested in a microscope with a polarizer and analyzer. So this is it, and these are my liquid crystal molecules. And when I give the electric field, you can see the way they are oriented. When they are oriented like this, the no light is allowed to pass through it. And here, so that is the reason. So why the light is being hindered with voltage? It is just because the molecules are oriented towards with the electric field, applied electric field, and hence in one particular direction light is passing. You can see it here. In another particular direction, light is not passing. This is what we call the modeling which we have proposed, and of course it was published. Then we come to memory storage. What is memory storage? Usually, a physicist, if you ask any physicist, what is a memory storage? How we demonstrate memory storage? This is what we call a very, very peculiar phenomena. That is, you take a sample and you just increase the field, and if it doesn't retrace the path, and when you decrease the field, if it doesn't retrace the path, then there is no memory effect in it. But you see here, when we decrease the field, we have what we call a hysteresis loop. A loop is formed. So this is a clear sheet. So this is what we call the dielectric hysteresis. We have measured the capacitance, with the permittivity, and we have varied the field. And when we increase and decrease, you can see the hysteresis loop. So more the hysteresis loop, more memory can be stored. So this is the increasing and the decreasing field. I have done it with many samples. You can see all these here. And I can show you one more. This is a sample where this is the nomenclature of the sample. And you can see here, this is what we call the field, which is increased, and this is a decreasing field, and a huge reminiscent field is there. So this can be used as what we call memory storage. These are memory storage devices. You can use them. Of course, you should have a chiral carbon. That is, these substances, when they are ferroelectric, then they'll show what we call the memory storage. Not all substances, a few of them can be used for memory storage. I can show you a different what we call pictures. This is again with multi-wall carbon nanotubes. We have tried the same experiment with doping multi-wall carbon nanotubes. So when we have doped multi-wall carbon nanotubes, what actually we expect? We expect the memory to enhance, and that has happened. So instead of taking the permittivity, instead of taking the dielectric hysteresis, I had seen the conductance, because that is what the multi-wall carbon nanotubes are known for. They increases the conductance. Not only they increase the conductance here, they also increased the loop, hysteresis loop, that can be seen. To make it more elegant, I had done it. I took a liquid crystal sample and had done the same experiment. There is no hysteresis loop at all. But when we have doped multi-wall carbon nanotubes, you can see the significant hysteresis. So even in a ferroelectric liquid crystal, if it is doped with multi-wall carbon nanotubes, the memory effect is substantially high. So this is what I can show you here. And I can show you another where you can see with the multi-wall carbon nanotubes, huge memory hysteresis loop can be seen. So without this, the extent, the area of the loop is not this much. So with the help of multi-wall carbon nanotubes, we can enhance greatly the memory capability. You can see, I can show you one more. So this is another, this is not with any multi-wall carbon nanotubes. This is with adipic acid, and we have taken the benzoic acids, and this is the molecular structure, and we have done the dielectric hysteresis. You can see it is not retracing the path, and there is a significant what we call hysteresis. And seeing, so we have done it with many. I just wanted to. So all these, whether it is with multi-wall carbon nano or whether it is without multi-wall carbon nano, we can use the what we call liquid crystals, ferroelectric liquid crystals for storage, memory storage. This is what we call the memory storage application of liquid crystals. In fact, I went a step ahead and had seen the optical memory. What is optical memory? You see, this is a texture of a liquid crystal. and I had given the voltage to it. You can see the stripes. And when I withdrawn the voltage, again the same texture is coming. So what do you infer by it? We see in electronics, in digital electronics, the memory storage stored in zeros and ones. So here the dark region and the bright region can be segregated, and you can see one as the bright region as 1, that is logic 1, which is representing 0 to 5 volts, and the dark region is 0, which is logic 0. So here the storage of memory. How is this storage of memory happening? Just to give a pulse. If you give an electric pulse, this is, and remove the electric pulse, this memory is not losing. It's still there. How do you erase it? We can erase it by taking it to the isotope. So this optical memory has been tested in many ferroelectric crystals, and we are successful in showcasing the optical memory. I'll show you one more. You see here the same. This is the texture, and when we give the memory, you can see the streaks. You can see the streaks which can be used as what we call zeros and ones, and this is the optical memory storage. And I can show you one more. This is what we call, again, with what we call as the field is increased, the dielectric. And here we come across a new phenomenon which is called parachromatism. So what is parachromatism? You can see here that the color of the texture changes, but the texture remains the same. Here it is green, here it is red. As we increase the voltage, what's happening? The color of the texture is changed. So these can be used, in fact, for such purposes. So if you want to measure the voltage, you can see the color and you can tell. So this is another application of liquid crystal. Now, I want to tell you another interesting application of liquid crystal. These are excellent filters. You can see the frequency and the gain. We have plotted a spectrum. We have increased the gain frequency from 5 to 11, and then we have measured the gain. You can see peaks which are the what we call characteristic peaks of the filtering. You can see these. In fact, there are 3 types of filter. This is called a band pass filter. That is, this is the pass band. These are the pass band, and this is the stop band. At this band, the frequencies are not allowed to pass. You can see all these, and you can vary this frequency. Here we got it in gigahertz, 875 gigahertz, and the bandwidth, the width, the stop, the region where filtering happens is around 72 gigahertz. So these are excellent filters, which has not been studied in any of the literature. So we can use liquid crystals as filters, and you can vary the filtering frequency by changing the composition of the liquid crystal. So this is what we call the liquid crystal. How we can, I had drawn an equivalent circuit. This is IR source, this is resistance, LC. These are LC filters. F is equal to 1 by 2 pi root LC. This is the formula. And then through that we have done this. So this is another application where you can exploit the liquid crystal for what we call filtering application. And I had one more. This is out of context. You can form Newton rings using the liquid crystals. You can see here bright rings. These Newton rings are supposed to be black and white. Why we got it in color? The reason is we have used polychromatic. If you use a monochromatic light, you can get what we call the first order, second order, third order, so on and so forth, that bright and dark. But since we have used it as a what we call polychromatic light, you are seeing beautiful colors over here. And then I told you here, this is parachromatism. Here, this parachromatism, you can see that these are the 4 brushes of liquid crystal. 2 colors are seen. Just varying there, we have varied the field. Here, we have varied the temperature. Just by varying the temperature, you can see the texture remains the same, but the color varies. So this is what we call the parachromatism. This is probably one of the most exciting application, because you can know the temperature. You need not go to a device. You need not go to a sensor. You can use the liquid crystal as a sensor. Seeing the color, You can assess the temperature. There are places where we need to do it just by seeing the color. And so this can be done. This can be done using liquid crystals. And I'll come to the last application of it. This is what we call, we have published in IEEE transaction. We have used liquid crystal as a thermistor. Now, what is the ingredient of thermistor? The ingredient of thermistor obviously is semiconductor. So here we have taken a glass plate, we have taken the liquid crystal cell, we have filled the liquid crystal cell with the liquid crystal mesogen, and then we have made the electrodes. And then we have characterized, we have seen the IV characteristics. This is the current and the voltage. We have taken two samples. You can see the two samples. One is, you can know there are two types of thermistors, that is the positive coefficient and the negative coefficient. So these both are achieved using two different types of liquid crystals. So this is room temperature liquid crystal, which I call RTFLC. So this is the room temperature where you have the negative slope and you have the positive slope for another liquid crystal. So these in the history of liquid crystal, this is the first time that we have done a thermistor. In fact, this has been demonstrated in a conference which was conducted by Sabu Thomas in Kerala, in his university. There we have demonstrated these graphs. Later on, we have published it. So this is one of the very, very interesting application of liquid crystal, where you can use it for what we call a thermistor. You can replace the thermistor. You can use the liquid crystal as a thermistor. The reason for replacement of semiconductor material with liquid crystal is liquid crystals are more stable. Liquid crystals are very cheap. And you know, the thermistors, if you take the commercial thermistors, they are bulky, they are very, you cannot, they come in a peculiar shape. Now here, liquid crystal is very flat. The thickness of this is the glass slide. So you can use wherever you want, you can insert it, you can make the thermistor the way you want. So this is an elegant application of thermistor, a new field which we have seen. And I conclude my talk. You see, we have filed many patents. You see, we have made optical shutters, we have made what we call hydrogen bond, using hydrogen liquid crystals, we have made light modulators, we have made memory devices, we can use liquid crystals as capacitance, we can use them to retrieve the electrical impulse, we can use them for filtering, we have notch filter, we have band pass filters, we can use as a diffraction grating. If you send the liquid crystal, if you send a light beam through the liquid crystal, it can be used as a grating element. You can use liquid crystal for thermistors. You can use them as thermally controlled switches. You can use them as low pass filters. You can use them as resistors. You can use them as ferroelectric switches. Then you can use them to derive the helical pitch. You can use them for positive and negative coefficient thermistors. And you can use many, many ways. These are all the patents which we have filed in recent time, and a few are granted, a few are published, and the others are. So this is, I want to thank acknowledgements. I want to thank the organizing committee. I want to thank the patron of this IKTBN CPAC, the director. I want to thank the advisor who is of this conference, and I want to thank the Kaushik Paul, the convener, Dinakaran Narayanan, the conference chairman, and Nidhi, the co-convener, and Ranjit Singh, that is the technical setup for the website. I want to thank my institute, that is the Banariaman Institute of Technology, and the fund given by the Science Engineering Research Board, New Delhi. And also I want to thank all my scholars who enabled me to do this work. And obviously at the end, I want to thank the Almighty. And thank you for your patient listening. And if you have any questions, I'm here to answer.
Thank you, Doctor. Is there any question from the audience? Please. Whoever is here to answer the question. By the way, overall thought, thank you, Doctor, for the talk and our body still has no, this is not only for display, it is image application is administered by doctors. If I'm not mistaken, there is application. We can make use from the register through its characteristic, which is control, well, we control it by whereby light capacity and what and so on. So also, it also will be used as a program we can build. There will be a lot of applications that we can from that side. So once again, is there any question from the audience? So yes, yes, all doctor. Again, thank you, doctor. Dr. Martin Mohan from Institute of Technology India on the topic of hydrogen for thermoscopic system, optical and electrical application. Thank you, doctor.
Thank you so much, sir. Thank you.
Thank you, Dr. Madhumohan, for your wonderful explanation, and Mr. Hamdan for chair this session. I would like to ask Dr. Madhu, would you like to be the chairperson for Dr. Jignesh Kumar lecture?
Oh, sure, ma'am. No problem.
Thank you. We move on to the next presenter, Dr. Jignesh Kumar Virohit from National Institute of Technology, India, to speak on material spectroscopic analysis. I would like to invite Dr. Madhumohan to chair this session.
Well, I invite Dr. Jignesh Kumar V. Rohit, Assistant Professor, Department of Chemistry, NIT, to talk about nanomaterials in spectroscopic analysis. Sir, the dais is yours.
Hello. I am audible. I am audible, sir.
Yes, sir. You are audible. Please go ahead.
Thank you, Professor, for inviting me. And before starting my lecture, I would like to congratulate organizer of this conference to organize such kind of event in such a pandemic time. And so, with this congratulations, I'm starting to my talk. So my slides are visible.
No, sir. No, they are not visible.
Okay, sorry, very sorry for interruption, sir. Uh, this conference, I'm Dr. Jignesh from working at the Department of Chemistry, National Institute of Technology, Srinagar, GMT, India. And today I would like to discuss about the nanomaterials in spectroscopic analysis. Uh, Nanomaterials in spectroscopic analysis. These are the outlines of my presentation. First, we will talk of the lack in simple spectroscopic techniques about nanomaterials based on the sensors. Then we will discuss somewhat about on individual spectroscopy and fluorescence techniques. Uh, why I decided to talk on particular this topic particularly because particularly if we are considering in India or IIT, NITs or central universities or centrally funded research lab or if it is state universities, Department of State University or highly reputed colleges, they all are having the very good infrastructure for research nowadays, I can say, and all of having the equipped lab also we can do some work and we can publish and all kinds of things. But here I'm talking about the problems of some small colleges or some university affiliated colleges. They are struggling to publish because they don't have that much instrumentation of character for characterization and all kinds of things. Not to talking or address particular this problem, but here my idea is to present this small instrument which all of the I can say your colleges are having because they are having the master's program, they are having the BTech program. They are using this simple usable spectrophotometer and sometimes they are using the fluorometer if they are talking about any medical colleges. They are having all these small instruments. But what problem they are facing because these instruments are very simple. So it is very difficult to publish a high impact paper, I can say, by using these two as main instruments. Okay. So because they are having the lack of sensitivity, lack of sensitivity, then question arise nowadays. Someone will told me nowadays using spectrophotometer or fluorometer having the higher sensitivity. I'm not talking about these high-end instruments because this high-end instrument is cost is more because normal colleges are not able to offer these high-end instruments because if you are purchasing the high-end usable spectrophotometer, it costs around 15 to 20 lakhs. So normal usable spectrophotometer is having the somewhat lack of sensitivity and sensitivity ranges between 10 raised to minus 2 to 10 raised to minus 4 molar. Lack of selectivity also I can say when we are talking about the sensitivity, high end sensitivity, then it is again is the lack of sensitivity is also there. And sometimes interference, because it is not that much high end instrument. So if there is the interfering species are also there with the analyte. So it is very difficult to analyze particular or it is very difficult to selective towards the particular analytes also. So now my idea comes how we can use these simple instruments and we can remove these lack, like we can remove the lack of sensitivity, lack of selectivity, and lack of interference. And then we can use this simple instrument to publish our paper in, and we can do, it is not an idea of publication only, so we can do the good research. Okay. So the integration of nanomaterial means combination of nanomaterial with this simple instrument. So we can enhance the ability of this simple instrument to as like the sophisticated instrument. This is the basic idea. Means the combination both nanomaterial as well as this simple instrument. So the sensitivity of this simple instrument, the selectivity of this instrument, the simple instrument is like one sophisticated instrument. This is the main idea behind my talk. So first we will discuss about somewhat about the nanomaterial, some basic things about the nanomaterial. So we can get the idea how each property of nanomaterial we can use to combine with this instrument and we can analyze our analyze. Okay. This is the simple, this is the nanomaterial. Nanomaterial means material within the any dimension within the 100 nanometer, and their size is less than the virus and bacteria. Okay. Is the synthesis of nanomaterial as we all about aware about this the bottom up and top down approach. This is the zero dimensional, one dimensional and two dimensional nanomaterial. Here we are focusing particular about the zero dimensional nanomaterial like nanoparticles and quantum dots and carbon dots particularly because this simple we can easy to see the very easy to synthesize compared to this one dimensional and two dimensional things we required some specific instruments in the environment. So their idea is to use the zero-dimensional nanomaterial like nanoparticle and quantum dot for the easy synthesis and easy availability. So these are the physico-chemical properties of nanoparticle as in previous lecture we already shown the various physical properties of nanoparticle. Here is the chemical property and particularly these are the chemical properties also which we can use to improve the sensitivity particularly. Okay. In particularly uh, in this all these properties, particularly we are very interesting about this optical property. First one, optical property. Why we are very much interested in optical property? Because by using this optical property, we are planning to develop our sensors and we are planning to integrate this nanomaterial with this UV visible and spectrophotometers to enhance their selectivity and sensitivity. That's it. In optical property, this the one phenomena is very common. I think you all heard about this. It is one is the surface plasmon resonance. Okay. Localized surface plasmon resonance, particularly. What is this localized surface plasmon resonance? Okay, this is the whole part. This is the dipolar excitation. I can say dipolar excitation between the negatively charged electron and positively charged lattice. Okay, and due to these LSPR properties of nanoparticle, particularly of nanomaterial, we can see the colors of nanomaterial. As we can see, particularly the related as we decrease the size here, I think in next image, there we can see the color of nanoparticle here in image B. You can find the color of gold nanoparticle with different sizes. Okay, these are things. One thing as we can modified the sizes, you can see two different colors of the nanomaterial. Okay. According to my theory, according to my theory, here you can see this equation x is particular phenomenon, x is equal to kr and r is the radius of nanoparticle. Okay. Means if we change the radius, means if we change the size of the nanoparticle, we can see the different absorption spectra. Okay. Here you can find the same nanomaterial is the gold nanoparticle with the absorption with the size of 22 nanometer, 48 nanometer, and 99 nanometer. You can find the different spectra as well as the different colors of the nanomaterial or gold nanoparticle according to their sizes. Okay. And in particularly sensor development, here we also incorporate one another theory that is called as developed by the Maxwell Garnet. Is the theory explaining the aggregation of nanomaterial. Is the aggregation of nanoparticle. Why we I discussing here the aggregation as well as the well discussed nanoparticle because in upcoming slides I'm going to discuss how this dispersion of nanomaterial changes to aggregation. Okay, and how these phenomena is help us to develop the sensors and how we can use this nanomaterial in these simple instruments. Okay. Also, when we are talking about the means, first I told you we are talking about the zero-dimensional nanomaterial, the nanoparticle as well as the quantum dot. And if we are talking about the quantum dot, I think this phenomena or quantum confinement effect. Okay, as we decrease the size of nanomaterial, okay, as the band gap increases between or you can say the electron transfer from valence band to conduction band and this charge transfer is increasing when we are talking about the from bulk material to nanoscale material. Okay. As we can see, there is a different variation in size of different quantum dot or nanomaterial. Here the optical spectra also you can see there is the shifting. If we are changing the size, there is the shifting towards the higher energy. and we can use this phenomena also to develop the sensor. Okay. Now, main question: why these nanoparticles are particularly used for the sensing purpose? Okay. As nanoparticles having the higher ratio of scattering to extinction, okay, extremely high field of enhancement, large surface area for functionalization, and for developing the sensor, this one is the very important phenomena, large surface area for functionalization or surface to volume ratio. Someone is calling the surface to volume ratio, sharper extinction band, then particularly narrow photoillumination band with higher extension coefficient and large surface to volume ratio. These all are the reason why we are using particular nanoparticles or you can say the zero dimension media for the sensing purpose. Okay. Now question is how this nanoparticle based detection system is working. Uh, when these nanoparticles, particularly nanoparticles, act as a transducer. Nanoparticles are act as a transducer. They are having this recognizing element, or you can say functionalizing element on the surface. It is either maybe organic molecule or any kind of molecule, which are acting as a catching element. Which are acting as a catching element. Particularly, nanoparticle is not able to catch the anything, right? So we are incorporating organic molecules of or some kind of the catching element which catch the analyte. Okay. Then this catching element catching the analyte particularly, then these nanoparticles giving the response. These nanoparticles giving the response. Okay. Then this response in terms of the changing in scattering property of nanoparticle, changing in conductivity of nanoparticle. Okay, regarding conductivity, in last lecture we already seen how this conductivity of nanoparticle help to develop the various or by using the conductivity property of nanoparticle, how we can use in different areas. Okay. If and then if it is changing in surface plasmon property or change in fluorescence property or change in redox property. Okay. Then this particularly analyte is bind towards the recognizing element which already bound with this nano or bound on nanoparticle surfaces. These nanoparticles giving the responses or nanoparticles giving the signals. Okay, which signals we can able to import, which signals we can able to import. So we can know our yes, it is in a particular analyte is bound towards this recognizing element or catching element because we can by normal it is not possible to give this binding event or catching event, but nanoparticles are giving responses. So by seeing this response, we can see this the bind or we can confirm this binding event with light and this recognizing element or catching element. Okay. Nanoparticles as optical sensors. Okay, nanoparticle, we can use this nanoparticle as a for preparation of sensors. Okay. If we are if there is a changing in the plasmon properties or change in absorbance property or we can say there is the colorimetric sensors as well as the reflective sensors. These are two types of sensors are there. If there is a change in fluorescence properties of nanoparticle during this catching event, then we can able to develop two types of the sensors, particularly called fluorescence sensing sensors, as well as or fluorescence resonance energy transfer based sensors. Okay. If there is the scattering change in scattering property of change in scattering phenomena, then we can able to develop these sensor based on the SERS, Raman scattering based and or this relay light scattering based sensors. Okay. But here we are not talking about this Raman based instrumentation. We are talking about this changing in colors or changing in localized plasmon property and as well as changing in the fluorescence quenching property. Then UV visible spectroscopy in LSPR based nanosensor. Now main topic for because in earlier slide basically I discussed how we can use this nanomaterial for sensing purpose. Now this is the real time application you can see. Here we synthesize or synthesis of nanoparticle also we can confirm using this UV visible simple UV spectroscopy to help us to demonstrate the synthesis of particular nanomaterial. Here in this image you can find the synthesis of simple silver nanoparticle, and when we find this simple silver nanoparticle, or we can incorporate this sulfur and phenolic acid, high carbon of sulfur and phenolic acid on silver nanoparticle, this absorbance spectra is slightly changed towards the higher C. And it is also confirmed by these dynamic light scattering images. Okay. And here is the real-time application. Here I use particularly this light carbamate of paracarceric butyl calixarin, paracarceric butyl calixarin. Okay. Particularly calixarin moiety. I think you already heard about this calixarin with we can use as a host molecule. So we incorporated this calixarin moiety on surfaces of nanoparticles, and particularly these act as a catching agent. Uh, Catching agent. Okay. And when this catching calixarin moiety is bind towards the particular pesticide that is the metsulfuron methyl. Okay. So this nanoparticle gives the responses. Here you can see there is a change in color. There is a change in color when we add all these different pesticides into the solution. The solution means nanoparticle with this binding moiety, and here in this case we use the calixarin. This calixarin bound is gold nanoparticle. And when we are analyzing all these pesticides, then only hexapidan methyl is giving the color change, is the visual color change. And by using this simple UV visible spectroscopy, we can get the confirmation by because only for this hexapidan methyl UV visible spectra is shift towards the, or you can say red shift or shift towards the higher wavelength. So here in first slide already discussed, here the selectivity. See, all these pesticides, and among these widely used the herbicides, particular pesticides, also is the class herbicides. The widely used herbicides, only these sensors is able to detect this particular pesticides only, because means because we are able to detect the selectivity, and we can able to increase the selectivity by doing this. We are able to able to increase the selectivity. Acha. If we are not incorporating this nanomaterial system with the UV visible, and before incorporating, if we are measuring the UV visible absorbance spectra of all these pesticides, okay, we are not able to differentiate. We are not able to differentiate. In particularly with a similar structure, we can find some of similar structure like this sulfosulfuron or this isopropuron. This some of the similar structure. So they are giving the similar absorbance spectra. We cannot differentiate if this particular pesticide is present in our food or food sample or not. Okay. But here by incorporating this nanomaterial based system, here we can selectively measure or selectively detect particular analytes. Okay, selectively detect particular analytes. Here this is the system. Okay, here what I got here is the complete system. This red part is the nanoparticle, and this yellow is our paracarceric calixarin, which is on surfaces of nanomaterial. And when this calyx moiety in fact, particularly with this metsulfuron methyl, okay, metsulfuron methyl is able to incorporate between this calyx cavity, and we can see this well dispersed nanoparticle is now aggregate. Well dispersed nanoparticle is now aggregate, and due to this aggregation, only you can see the visible color change as well as the change in visible spectrum. Change in visible spectrum. So this is the main funda we are using to analyze. We are using to determine various analytes. Okay, and here we can able to determine, or we can able to confirm all these things using simple usable spectroscopy. But for more confirmation, we are using this dynamic light scattering and as well as this transmission electron microscopy just for the more confirmation. Okay. Here you can see this bare nanoparticle having the size of 13 nanometer. It increases when we incorporate mighty like this paraconsiderable, just slightly increase. But when it interacts with this pesticide, it completely aggregate and size, we can see size regulate more, Here you can see, you see from this image with the well-dispersed nanoparticle is now completely completed and comes to close to each other and this is into complete replication. With the, I talked about the selectivity, how we can increase the selectivity of the simple UV spectroscopy by integrating the nanomaterial. Okay. Now I am talking about the sensitivity of material-based system. Okay. Here you can see here by this spectrum, or here you can see the analyzing the useful spectroscopy. And here you can see that this usable spectroscopy based method comparison you can see is the performance of this simple usable spectroscopy is now equal to HPLC, GC and voltammetric method equal to. Okay, means you can use the nanometric based integrated system, uh, simple usable spectroscopy, and performance of simple usable spectroscopy is now being achieved like GC, HPLC, and some voltammetric method. This is the beauty of integration of nanometric with this simple usable spectroscopy method. Okay. And this is the last thing how we can remove or if there is the interfering species are also available, then also this system is working very specifically, very specifically. This is the one system with some molecules with hydrobenzoic like some molecules incorporated on the nanoparticle surfaces, okay, and develop the sensor for analysis of these higher protein pesticides. Okay. When we incorporate this system is particularly selected towards the higher pesticides. When we are adding all pesticides, it is not even very much. Even if higher flow pesticides with the mixture of other pesticides, okay, it is not giving responses for all other pesticides, even with the pesticides mixture. It is only giving the responses for particularly higher flow pest. This is the how we can in presence of interfering species also increase the response. Then again, I am discussing one another use of usable spectroscopy. As usable spectroscopy is not that much complicated instrument, and particularly optics based usable spectroscopy is very simple instrument, just having the sources and the one detector. Here the sources and detector and the sample period. Okay. So we can do lot of modification. If there is a very complex system, we cannot to open ourselves like HPLC, GC, DG, or DSC. We cannot to open ourselves because we needed some expertise, engineers here are there. But as this usable spectroscopy is very simple instrument, we can open and we can play with it. Okay. Here we give because in normal usable spectroscopy, we need at least 2 ml or 2 to 3 ml sample per analysis. And as to cost cross-cutting and to consume less sample volume, we minimize it. Okay, and first we are using this microcube. This is the not important things because we can purchase these microcubettes. Okay, but here in microcuvette also, at least we need 800 microliters of sample. We need 800 microliters of sample. So what we did, we inserted one wooden piece inside this sample tube. And particularly we see these optical lights is not interacting with the wooden cuvette, but to height up the cuvette, we just incorporated this wooden piece. Okay, so this height of the cuvette is up. Okay, now instead of 800 microliters, we use 150 microliters, 800 to 150 microliters. And if you are talking about the normal usable or normal any something method, okay, with a very less volume. Okay, in SPLC and BCI, with a very 50 microliter or 25 microliter also. No? But here also we can play and we can do the minimization of utilization, minimization of, or you can say the miniaturization, in which we can minimize the sample volume. But the things to discuss this image or this thing is a very simple instrument, so we can play with it and we can we can do the many modifications. Okay. Now, here's the last part of the discussion: how this fluorescence spectroscopy is used for this. Fluorescence spectroscopy is used for sensing wave sensor. Okay. Synthesis of quantum dots or carbon dots also confirm that using this fluorescence-based technique. Okay, why am I talking about this fluorescence-based technique? Because many medical colleges or nursing colleges are using this simple spectrophotometer for their practicals. So this kind of the simple spectrophotometer they can use to do the high quality of work, or they can by using the simple instrument they can publish in high impact journals. Okay, these also here you can see particularly carbon dots. Okay, carbon dots synthesized on the citadel. Okay, carbon dots synthesized on citadel. Okay, and we added different metal ions. Okay, different metal ions, and only the system is selected. System is selected towards the copper. System is particularly selected towards the copper. We are the only decreasing intensity of copper input instead of all other metal ions. So this system is particularly selected towards the copper. Here also you can see the sensitivity. Okay, this system is able to detect the copper up to 0.01 micromolar. 0.01 micromolar means in nanomolar range. So in this way, we can be able to enhance the selectivity as well as the sensitivity of simple spectrophoto. And this the basic things what which I want to discuss, how we can use this nanomaterial and use this simple instrument, and we can do or we can start our research with this. But not where I didn't show is high quality of research work, or we can use it. So we are working on confocal microscope and all kinds of the things. But here I try to show some simple kind of the things. So someone wants to start their research work in less facility, they can start and do their research work. Uh, Here, I would like to acknowledge my supervisor. From I learned with all these techniques, and I did my PhD under him, as well as one of my colleagues. Because what I shown is fluorescence kind of thing is what I worked for. Is my current institute, NIT Srinagar, where I am working, and particularly we are basically we are focusing nowadays also to use of nanomaterial in analytical chemistry. How we can use our nanomaterial in analytical chemistry, and the improvement of sensitivity and selectivity of simple instrument is the major focus area of our research. Thank you for your kind attention. Thank the organizer for providing me opportunity to speak in front of all of you. Thank you. Please give everyone and please.
Thank you, Dr. J.V. Rohit, for your lecture on nanoparticle-based sensors. In fact, your UV spectroscopy for microvolume samples is exciting. Also, your fluorescent spectroscopy, the sensitivity of the CD-based sensors is highly appreciated. And I congratulate you on taking pain in going to the nook and corner of the country where they can uh, get some instruments with a small amount of budget. And thank you for your wonderful lecture. And the floor is open for questions. If the audience have any questions, they can ask Dr. J.V. Rohit and get it clarified. Thank you.
May I ask one question, please?
Please go ahead, ma'am.
You said that you use many molecules for precise detection using spectroscopy. I just wanted to know if you use any specific linker to conjugate these nanoparticles to the analyte, or this is overnight incubation.
No. We are using the means we are using the molecules. So, we are interpreting molecules, organic molecule on surfaces of nanoparticle. It is being used to go more than one thing. It is act as a linker also. It is act as a binding binder also with our analyte as well as the linker also. So, like we can find this nanoparticle instant aggregation. We are not keeping this system
Okay.
aggregation for 1 hour or 2 hours. Instant, when we
Okay.
are adding, it is showing the aggregation because this molecule on surfaces of nanoparticle and also one more important thing which I also forgot to discuss during the session. This molecule provides also the stability of nanoparticle. Means once we prepare this system, nanoparticle functionalized system, we can use this nanoparticle for I think more than 1 week. So it provides the
Okay.
stability of the sensor also.
Okay, what will happen if suppose more than one or more than two analytes are present in one solution?
First, man, we are detecting separate, and if it is
Okay.
showing that yeah, if it is in more than one amount is there, but means if we are talking three metal ion is there in our
Yes.
sample, this magnesium, calcium as well as the copper. Okay, so first we are analyzing separately. We are adding magnesium. It is not showing color as well as spectral
Mm.
changes. Means it is not selective or it is not sensor for the magnesium. Then we are adding calcium separately. Yeah, and if we are developing sensors for copper, it is only showing the changes with the copper. Okay. And then
Mm-hmm.
we are adding the P. Then it is also showing the similar spectra as it is showing in when we are analyzing single copper. So we can say it is
Okay.
selected towards the copper.
And what will happen if suppose more than one is giving you a typical spectra? Then will you get more than one typical spectra for that, or it will be some other shifting in the P?
No, no, madam. Particularly in nanoparticle based system, I can say it is not giving one or more than one spectra. It is giving just a changing. Yes, it is called nanoparticle is going 3.420
Yeah, it
nanometers.
is
It is
shift.
just
Yes.
shifting only.
Mhm. Okay then. Okay, thank you.
Sir, I have a question. Dr. Rohit, do you synthesize the nanoparticles or you procure it from the market?
No, 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 sir. We are synthesizing only. We are synthesizing only by using simple method. If we are using these silver nanoparticle just we are taking this Iscmnb what is available in PG or UG lab and we are just adding this sodium borohydrate and like that simple reducing the then we are synthesizing.
Oh, that's great. That's great. Do you characterize it in because if you buy from the outside, the parameters are already given, the length, so on and so forth. When
No,
you
no,
make
sir,
it,
sir. In my slides I shown, we already characterize and confirm. We are taking confirmation for of using transmission electron microscopy, size confirmation, and all kind
good,
of
good.
this.
I understand.
Transmission electron microscopy and as well as dynamic light spectroscopy.
Very
We
good.
are
Very good. Then, how do you use a sonicator to disperse the what is the technique? Because there are functional nano carbon tubes, and you may be knowing it. So, what is the methodology? Do you use functional nanotubes also?
No, 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 sir. We are not using functional nanotube. Particularly, under behind is using this zero-dimensional nanometer, which is the nanoparticle, particularly silver, gold, copper, as well as the carbon dots. What is the beauty of this simple material is that they are already in dispersed form only. When we are synthesizing simple silver nanoparticle, we no need to use the sonic and all kind of things. They are in water dispersed and well dispersed, I think so. So they
Okay.
are already water dispersed.
Very good, sir. In fact, I want to collaborate with you. We'll be talking it later on. Thank you so much.
Okay.
Thank you so much.
It's my pleasure, sir. It's my pleasure.
Great. Thank you. I think there are no other questions. I request the organizers to take over. Thank you.
Thank you, Dr. Madhu Rohit, for the interesting presentation, and Dr. Madhu Mohan for chair session. I would like to ask Dr. Rohit, would you like to be the chairperson for the next lecture?
Okay, madam. but I have to see the new coming with I have to see who is the speaker. Because the previous time didn't have to be chairman. But I will
Yeah.
send I will send.
Okay. We move on to the next presenter, Dr. Nandini Sharma from Punjab Technical University, India, to present about usefulness of wide bandgap metal oxide for photocatalysis. I would like to invite Dr. Jignesh Kumar to chair the session. Thank you.
Hello.
Hello.
Yeah. Am I audible?
Yes. Yeah, okay.
So may I start the presentation now?
Okay, 1 minute, madam. I will introduce you.
Okay.
Uh, Here, I would like to invite Nandini Sharma from Iscmnb Engineering College, Punjab Technical University, and she will talk on usefulness of white bandgap metal oxide for photocatalysis. So now I am handing to Nandini Sharma. Welcome, madam.
Hello everyone. So myself Nandini Sharma. I have been associated with the Department of Delhi University, Department of Physics in Delhi University for 5 years. Then a few year, 1 year back, I shifted to Punjab, so I joined the Punjab Technical University. So I'm presently working there as an assistant professor. It's been 5-6 months over here. So let me start sharing my presentation. Can you see my screen, my presentation?
Yeah, yeah.
That's okay.
Fine.
So today I will be talking about usefulness of wide bandgap metal oxide for photocatalysis. So before studying about that, because we are focusing on the wide bandgap metal oxides, which are actually semiconductor materials, but exactly what we are going to do, we are going to prepare the nanoparticles of these metal oxide materials to implement in the application of photocatalysis. So, as per the previous lecture talk, also nano was being discussed. So, nano is anything which is size ranging between 1 to 100 nanometer. We categorize it to be in the nano range or nano scale. That's it. Okay. So, and we know about how it is like different from the how the size varies in comparison to other materials which are existing in nature, like football or human hair. Their human hair is millimeter, football in centimeter, and RBCs are there in micrometer. Nano is even smaller than that. It is in nanometer, 10 to the minus 9 meter. And normally, within 100 nanometer, we call it as it's a nanoparticle. If any one dimension is lying in nano range, we call it's a nanomaterial. But the structure but the nanostructure that we name it does changes. Okay, so does we classify it based on its dimensionality? It's 3D, 2D, 1D, and 0D. 3D is a bulk material. This means all the 3 dimensions, they are not lying in the nano range. They are actually in the microns or somewhere like above 100 nanometer, we can say. So we call it a bulk material, 3D material, which we have been using since a very long time. But 2D is then if any one dimension is lying in the nano range, we call it as a 2D nanomaterial, like example nanosheets. And then comes a 1D if 2 dimensions, and then comes a 0D. So my work today is on the 0D, 0 dimensional nanomaterials. So I will be showing you how did I synthesize the 0 dimensional nanoparticle, or you can say all 3 dimensions were confined in the nano range, and even above that there's a nanostructure whose name is quantum dots. So I will show you how I synthesize the quantum dots of metal oxide material whose name is tin dioxide, and how its application was being observed in the photocatalysis, and how well it showed its efficiency in the degradation of various contaminants when it was exposed to the natural sunlight. So this is basically we will today focus on this 0 dimensional nanomaterial. So then why actually we all are moving towards the nanoscale? Because obviously the properties are getting enhanced when we are moving towards the nanoscale size. First of all, like if you see, because today's topic is my lecture is on catalysis. Obviously, catalytic property will get enhanced due to the change in the band structure, energy band structure. That is why the catalytic property get enhanced when we are moving from bulk towards the nano size material, and even moving from 2D to 1D to 0D. 0D is having much more higher efficiency, because in my thesis work also I compared it with the nano rods and nano wires also, but the quantum dots was showing the best catalytic efficiency in comparison to other nanostructures when observed and when implemented for this particular application. And other properties also gets enhanced, like electrical, magnetic, mechanical, optical. So these all properties can also be explored. So that is why we are moving towards from bulk towards a nano size, or we are moving from bulk towards the nanoscale materials, because obviously the properties are getting enhanced, and the main reason is it's a higher surface to volume ratio, because as we are breaking the bulk material into the nano size material, obviously there will be more particles, and when we calculate the specific surface area, or which is equal to surface upon volume ratio, that comes out to be a higher value. So that is why it is showing a better catalytic efficiency in comparison to others. Then it's an opposite or converse classification, like we discussed about the dimensionality. So quantum confinement is for the charge carriers. If charge carriers are allowed to move in one dimension, okay, so they are said to be in 2D, two-dimensional quantization, because they are easily moving in one dimension. If they are allowed to move in two dimensions, we say one-dimensional quantization. This is actually based on the Schrodinger's application, which says that particle in one box, which gives a formula equal to En is equal to n square h square upon 8ml square. So everything is correlated. So nano is easily explained by using the quantum mechanics. So I will be showing you further how, in the case of quantum dots, like if you talk about quantum dots, it's a three-dimensional quantization. So electrons can easily move in zero dimensions. So they are not allowed to move in any dimension, but yes, energy level will be discrete in nature, that is particle in 3D box. It is a simple example. Quantum dot is a simple example of the particle in 3D box that we studying quantum mechanics. So we will be, I will be just showing you how I synthesize in today's work that particular nanostructure particle in 3D box. So my focus for today's talk is the metal oxide quantum dots for critical analysis. So let's proceed on to what exactly is photocatalyst, because we know about the metal oxide and nanoparticles, but what exactly is photocatalyst? It is actually a catalyst material or any material which gets activated whenever a photon or light particles are incident on it. But there is a criteria for it to get activated or it to start working. So the basic condition for it to start work is if the light of incident radiation is greater than its band gap energy, Eg. If H nu is greater than Eg, like if you have a conduction band here, if you have a valence band out there, so the band gap will be Eg. Ec minus Ep is Eg, because this is G, then this is Ec level, and it extends towards the plus infinity. So we say that Eg is equal to Ec minus Eb, and whenever the particle is having energy greater than Eg, then yes, photoexcitation process will start. The photon is incident. What is photoexcitation actually? There is an electron hole pair in the valence band. That pair gets dissociated. Electron jumps to the conduction band, and a vacancy is being created in the valence band. So by doing that, what is happening is we are able to form a highly active materials or fatty materials. They can ionize the contaminants in the materials. I will show you further how it alters the chemical bonds, and excitation of semiconductor photocatalyst generates the exciton pair. This electron and hole pair are actually causing the reduction and oxidation of the contaminants with which it is reacting. So today, I will show you my work on the dye contaminant, and specifically for the using by dye that I will show you further slides. And why we are focusing on it, because obviously even in my work I use the natural sunlight as a source of energy, not the solar simulator or UV lamp as a source, but I use the natural sunlight, because river waters are actually getting deteriorated. They are getting I took some so they are getting so many kind of impurities in them. So even natural sunlight is available all over the place. We cannot have an artificial source of light to clean those rivers or waters for that. So for water cleaning purposes, this thing was being carried out in the natural sunlight such that we can see how effectively our catalyst is actually behaving or working in presence of natural sunlight, and then only we can configure it for the those river waters, because we took a small sample in our lab, so it was being given in the sunlight, actual sunlight, and we saw it performed. It showed a really good output. So I will let me show you. So I use the co-precipitation route to synthesize that nanoparticle. So these are various synthesis methods, top-down and bottom-up approach. So mine was a bottom-up approach. So chemical method used was co-precipitation method. Then okay. So co-precipitation method actually involves the simultaneous occurrence of nucleation, growth, cohesioning, and agglomeration process. Simply, you have a I use the a tan solution and an anion solution like tin chloride and lithium hydroxide was being used in my case, and then they were mixed by the sonicator, and also then uh, use the normal magnetic stirrer to rotate it, and that things for lithium hydroxide was injected into tin chloride solution dropwise by using the burette which was being installed above the beaker, and then after some time of stirring and heating, the reaction was being shown because some cloudy kind of material was being shown in the beaker. So this was how the exact concentration that I took for synthesis of these quantum dots. Tin chloride dihydride was used, and it was solvent was 100 ml of ethanol. It was stirred for 1 hour on magnetic stirrer. And then lithium hydroxide 1 molar was prepared in 200 ml of distilled water, and then it was slowly added to by using the burette. It was slowly added dropwise to tin chloride solution, and the pH value as measured by the pH meter was observed to be 6. Then solution was stirred for 1 hour for nucleation of tin oxide quantum dots, and it was showing a yellowish white color precipitate, and it was very cloudy when I saw it. So then it was filtered out and washed off, then it was dried and healed for this much amount of temperatures to see how the things change when I anneal at high temperatures also. So catalytic properties of all these materials, so which were annealed at 300, 400, 500, 700, 900 were being measured in the end to see how the crystallinity or how the size and how the structural agglomeration will affect the photocatalytic activity. So tin dioxide on which we are talking about is actually a wide bandgap semiconductor. Even ZNO and TiO2 are actually very much explored in this particular field. So I wanted to explore a new material, tin dioxide. It was very less work is done on that, and even the quantum dots of tin dioxide were when I did my work, it was not being done to that much extent. So I did something different during that time. So then this was the configuration in the month of April. I measured in the presence of natural sunlight how the catalyst loading was fixed to be 1 gram per liter, and degradation reaction was carried out at 40 to 45 degrees Celsius or temperature, which was being noted on that particular day in the summer of April. And degradation kinetics were observed, and eosin by dye solution concentration was there. It was like 0.0001 molar, or we can say in distilled water, and they were divided into 5 equal vials such that I can put it for some amount of hours and then note the how much amount of dye has been degraded after some period of time. Then this eosin wire dye photocatalyst source system was stored on magnetic stirrer for 10 minutes just to have that absorption-desorption equilibrium. So, and it was attained by keeping the black box. If there is some degradation or it's something happening in the they should get attached to each other and absorption-desorption equilibrium can be attained. So I kept those vials in the black box for 30 minutes such that they can adjust easily. Then they were being put onto the terrace, and it was measured at an interval of 20 minutes for 5 samples using UV vis, and for every 20 minutes, after every 20 minutes, uh, it was being transferred to the UV vis sample measurement unit such that I can note down its particular absorption, how much absorption is it is showing after each 20 minutes. And as the color, as the dye was getting degraded, even I could see that the color was becoming paler, and because of that, the UV vis absorption peak was decreasing. Then after every 20 minutes. Okay, then the samples were, and obviously we were also worried about that it may evaporate, because normally when you put clothes outside in sunlight, the colors evaporate. So we had covered our samples with a Duracell, it's a transparent Duracell sheet, such that it should not evaporate. But yes, we can actually provide sunlight to the photocatalysts also, and they can show their work and performance in degrading these dye solutions. Okay, these are the results of by showing that the S1 structure which was formed was a quantum dot, as you can see here. So XRD peaks were well matched with this with the standard ICD PDF card number 770447, and it was matching well with the quantum dots peaks which should be occurring at these particular back diffraction angles. And as we increased the annealing temperature, yes, peaks were enhanced. You could see the crystalline structure, which was getting enhanced with the increasing temperature. And Scherrer formula was used to calculate the crystallite size in every case. And even it is not actually very accurate one, so we also did some. We also got the HRTM done for our sample, and it was so beautifully photographs were being observed in that particular SEM image. And after we could see that at 300 degrees Celsius, when it was annealed, the size was 6 nanometers. Quantum dot is anything which is having size comparable to the Bohr exciton radius. And for if we talk about SNO2, the Bohr exciton radius is actually 2.7 nanometer. And if we double it up, the diameter comes out to be it comes out to be 5 nanometer. So 6 nanometer is actually comparable to the Bohr exciton radius. So it was termed to be the quantum dot. Then lattice parameters were calculated and cell volume. So as we keep, the simple thing is, as we kept on annealing it at higher temperature, size was observed to increase, and that's a normal phenomenon. So nothing strange was being observed, but yes, we were able to form quantum dot by maintaining the pH and by slowly pouring up the LiUL by using the burette and monitoring it throughout the reaction. So crystalline tetragonal rotile structure. This was being drawn. These were actually the parameters were input in the some software called the PAS software, which is actually available in the University Instrumentation Center at Delhi University. So there I carried out this particular thing. So I could draw this tetragonal rotile structure, which is the actual structure of tin oxide, and then the same images were recorded, but they were shown to be highly clustered. I was able to observe the highly clustering in the samples, and as the temperature was increased, the cluster formations were more bigger, because maybe the size of particles were getting enhanced or increased. But yes, they were clustered and agglomerated in nature. So, but yes, they could. We can see out here that we have a spherical kind of nature here, which is forming various clusters. So then in HRTM you will be able to see much more clear image. See here in S1 sample, this is a 5 nanometer scale. So as you can see here in the particles, and they're highly crystalline, because we are able to see the lines also in this particular image, and the particle is almost having the size here. Like, this much is like comparable if we use software to measure this by this particular scale. So this is approximately equal to 6 to 7 nanometer when we compare by the HRTM images. So it confirmed the formation of for the formation of the quantum dot structure in our particular thing. And so S1 was very uniform, and in estimated slide diameter of 6 nanometer, and clear lattice fringes were demonstrated, which presented the ultrafine nanoparticles. HRTMs proved clearly the formation of crystalline lattice and revealed the grain boundary region also. So, and they were found to, every sample was found to possess a crystalline nature, so that was a good thing, because we could see the peaks were not very sharp in the first case, so it could be a confusion that they are amorphous in nature. But yes, in the HR10 we got a very clear thing that obviously they are crystalline in nature because we are able to see the lattice fringes also, and they were they were then indexed as per the interplanar reef spacing. So this was how, and when the size was being increased, when the temperature was annealing temperature was increased, we could observe an increase in size. So here you can see for SNO2 SNO2 material, which is annealed at a higher temperature S3 sample. The scale is this 5 nanometer, but the size is quite high. So further we have a table for that, and more the temperature is increased, you can see a bigger size for this nanoparticle. It is having a pretty big size, almost 15 or 20 nanometer hoga iska, like it is around 15 nanometer. Okay, so this is how it was being confirmed by using the HR10 images, that how our size is being increased on increasing it at high temperature, and even the green boundaries came out to be more clear and distinctly observed. So, and these values were obtained from the index selected area electron diffraction pattern, and it further confirms the formation of the tetragonal rutile structure. And this is the main, which I was talking about. Here I have just got the UV vis spectra for the pure SNO2 samples to see how its energy band gap is actually varying. It's actually varying with the temperature increment. So obviously, as we increase the size, as we increase the size, the band gap decreases, and as we decrease the size, band gap decreases. So this is the quantum confinement effect. Normally, the band gap is around 3.8 electron volt, but it was observed to be 4.1 electron volt for S1 sample. That was due to the quantum confinement effect because we were able to form a quantum dot. So you can see here it's a big absorbance value in wavelength. This is an absorbance of alpha, which is about alpha actually holds here. Absorbance alpha, so it was being used here because HU, HC upon lambda, lambda benefit from here, and HU. When we plot this kind of graph, this is for measuring the band gap. Because as we take the tangent to this particular, we take a slope for this, we are able to get the band gap value. The slope gives the band gap value. And then how the variation of how the temperature affected the crystallite size and band gap. This was being shown in this particular diagram, and we were able to find out that band gap decreased on increasing temperature, but yes, crystallite size increased on increasing temperature. This is easily visible in this particular graph. Then again, the photoluminescence spectra were recorded, and we were able to observe some defect states and deep level emission states which were being reproduced as we are moving from quantum dots towards normal nanomaterial nanoparticles. So we could see that S1, which is a quantum dot. So quantum dot was showing the violet emission peaks which were not present in the PLS spectrum of the other samples because of quantum confinement effect, and it was observed for the S1 sample only, and they were quite broad and symmetric in nature. And because of that particular thing, maybe its photocatalytic activity was quite hindered in comparison to others, but we were quite sure that QD will be showing the best photocatalytic activity among all. But yes, here we could see that maybe that can be the reason, because it had deep level emission, intermediate levels happen with quantum dots. So maybe it will hinder the photocatalytic activity. So when the studies were being performed, and we were able to see that initially the S1 sample, that is a quantum dot, were showing to be they were showing a slow rate in the initial stage to degrade the dye molecule. When the last 20 minutes, we got a sudden shift from 40 to 60 minutes, you can see here. We could saw that the concentration, actually C is giving the final concentration similar to the initial concentration of dye molecules. So we could see that C by C0 concentration was shown to be least in this particular quantum dot sample. So this was a very different result, and we could see that S1 sample nanoparticles annealed at higher temperature showed lesser absorption of dye molecules and resulting in poor degradation performance. The rate was poor, but yes, similar to the other particles, they showed a good photodegradation efficiency, but the rate was quite slower in comparison to others, as you can see from this graphs. And this is actually the chemical equation that is it was in the first order rate kinetics equation. So we use this equation to get the rate constant value. The conclusions were quite clear because quantum dots showed the best efficiency, but yes, rate constant was not that much good because it in the end it degraded the most. It degraded the most of dye molecules, but yes, it was observed to be quite slower in comparison to others. And as you can see, S5 sample. S5 sample was moving a lot, like it was moving very well. So, in the end, what happened was it was, but still lagging behind the S1 sample. So we could see here S1 and S1 and S5 sample. Among the out of both the two samples, S1 was showing the best catalytic efficiency because it degraded the 73% of dye molecules. So quantum dots, because their structure is different, and also we can see the quantization in all three. So in all the three dimensions, they were having discrete energy level positioning, and because of that, electron charge carriers were able to flow easily without any hindrance. So that was the reason they showed a best photocatalytic efficiency. Not even that. If when I compared it with other results, which were being shown for the zinc oxide and TiO2, natural sunlight, they were not. They actually do not show this much amount of photocatalytic efficiency within the 60 minutes of time duration. So that time efficiency is much more lower. So quantum dot is actually a good material, and SNO2 is a SNO2 is actually a very good, and it's a biocompatible. It's not harmful, so it's also a good alternative to be used as photocatalyst. But right now, yes, ZNO and TiO2 are used at the most. So SNO2 can be a new possibility to be used as a wide bandgap photocatalyst. So these are the Nanotechnology Research Center, and here I worked in Department of Physics, Delhi University, and Netaji Subhash University of Technology, Delhi, where I did my both the research works. So thank you very much for your attention. If you have any question, you can ask me. Hello.
Hello.
Hello. Yes, sir.
Very nice presentation actually. You used the metal oxide based photocatalyst which is going to high efficiency, I can say. So first, this session is open for participants. From participants, you can actually ask them.
Hello, Nandini. I have one question, in fact, suggestion.
Okay.
Have you used these nanoparticles for field application?
Not for field applications, but yes, we took some sample from the river, which was having dye molecules in that. So, but the thing was the dye which we prepared in our lab, eosin Y dye, that was there in that particular lab material. But in river there were too many things, so we could not get a good result for that. We could not get a good result.
One more question is that if suppose you are able to use for field application, how will you remove these nanoparticles after its application?
The thing is, the main thing is we could have a like 2D nanomaterial. We can have a film of nanomaterial such onto the substrate, such that substrate can be taken outside and then it can be reused. That's the future prospects of using it as a to eliminate the dye molecule, the contaminants from the river, and then those substrates can be they can be reused by putting inside the river again. So nanoparticles cannot be removed. Obviously, they are so small. But yes, if a coating is being made, a thin film is being coated on the substrate, yes, a full sheet can be put inside that particular thing. But that also needs to be a polymer, or it needs to be hydrophobic in nature. Everything needs to be taken care of. But yes, it is highly proposed that if we do it in the future, that it's going to be a great thing because rivers are getting dirty day by day, and natural sunlight will be used for cleaning it. So it is going in. It's in
Okay.
yeah, not in
You can
not in
also
carry.
think of using the magnetic beads.
Yeah, okay. Then
Yeah.
iron oxide nanoparticles can be get, but I didn't work on iron oxide one because they can be
Okay.
attracted back. Then we can, yeah. I know.
Yeah. Because
I did
it is
one
being
student.
used.
Yeah. I made one student to do. I use aloe vera gel to synthesize nanoparticles of iron oxide. Yeah.
It's a good presentation. Yes.
Natural experiment sign of our so if you any measure the intensity of the light,
Solar simulator is there if you want to put an artificial sunlight or you want to see the difference of intensity of light at how it is behaving in different intensity of light. Solar simulator is there for that. We can optimize the intensity and then see how the catalyst is actually responding to that particular intensity of light. Yes, solar simulator is there. Yes, yes. Yes. No, I didn't try for SNO2. Actually, I had one student for dissertation. So I made her to synthesize the atoms and nanoparticles. And even so, I didn't try for SNO2. I did for Fe2O4, yeah, iron oxide. And it was well prepared. And if we could see the magnetization was so good, I could, by using magnetic field, like ma'am said, it was attracted towards the magnetic field. Everything got stick. They form a cluster and they arrange. They show a so good pattern. They arrange in different shapes. They move like when you have in when you store in a vial also. When you keep a magnet near to it, they got stick and go here and there. They have a very good magnetic property. But I didn't try for this. Yes. Yes, sir. No doubt. Thank you, sir. Thank you so much.
Thank you, Dr. Sharma, for the interesting presentation, and Dr. Jignesh Kumar for chair this session. I would like to ask Dr. Nandini, would you like to be the chairperson for the next lecture?
Sure, sure.
Move on to the next presenter, Dr. Anjana Pandey from Motilal Network, India, to present our student and investigation of Salmonella typhi Epidemic approach. I would like to invite Dr. Nandini Sharma to chair the session.
Hello, I would like to welcome Professor Anjana Pandey from Department of Biotechnology, that is MNIT Allahabad. It's a well-known institute in this area. So, and her topic of presentation is silver nanoparticles with detection of Salmonella typhi, a theranostic approach. So that seems to be quite interesting. So, ma'am, I welcome you to present your lecture.
Very good morning to all of you, and I congratulate the organizers for organizing such a nice conference in an online mode, because it's a tough time for everyone to be at home, to stuck at home and not attending the laboratory, but still we can do some research and talk about the research activities, whatever we have achieved. So, first of all, I would like to introduce myself that currently I'm a professor at Department of Biotechnology of Motilal Nehru National Institute of Technology, Ahmedabad. And it's a institute which is known for quality of excellence in academic pursuits. And it has been established in 1961 as one of the 17 regional engineering colleges of India. And now, it is has been granted as a status of institution of national importance since 2007, and we are offering BTech, 9 BTech and 19 MTech degree programs, including MCA, MBA, MSc, MSW programs. Hello, can you all hear me? Am I audible?
Yes, ma'am, you are audible. You are audible. So we are audible.
Fine. Fine. So, in this short introduction, I would like to come to my presentation. And as the title is that silver nanoparticles, we have prepared silver nanoparticles and we studied its therapeutic aspects as well as the diagnostic aspect. So, to introduce this subject, first of all, we should know that what is Salmonella typhi. It is one of the strain of Salmonella enterica. It is a rod-shaped bacteria which is highly mobile, and it is gram-negative by nature, and it is facultative aerobic as well as it is flagellated, and it causes the typhoid fever. Typhoid fever, you know that the symptom of typhoid fever include nausea, vomiting, fever, and death. And it can only infect humans, and no other host has been identified. And the main source of this typhoid infection is swallowing infected water. And sometimes food are also contaminated with this S typhi if it is not properly washed or irrigated with contaminants. You know that this Salmonella typhi reach our intestinal barrier through the specialized M cells. These are the microfold cells, and the specific structure of its virulence factor, which is having the lipopolysaccharides, and that plays antigenic behavior as well. And beside that, this is the endotoxins. You can see in this picture that some soluble enterotoxins which leads to the diarrhea, and beside that a lot of antigenic virulence factors are there, which is a part of the structure itself, and that actually inhibits the phagocytic killing by the host cells. So basically you see this bacteria has three types of antigens: O antigen, H antigen, and B6 antigen. And these antigens actually impart specific properties for its immunogenic properties. What happens actually when it enters into these M cells after ingestion through the food or contaminated water? That time actually it enters into it and it targets the basically our macrophage, as well as later on it disseminates through the lymphatics as well as the bloodstream to the different lymph nodes, as well as it enters into the deeper tissues. And if it is not being properly treated, then it may also be transported to the spleen, bone marrow, liver, as well as gallbladder. And it can persist for long our tissues and leads to the periodic reseeding of these mucosal surfaces. That's why there is a need to diagnose as well as treat it at the appropriate time. Even World Health Organization estimates this typhoid fever disease at 11 to 20 million cases annually, and it is taking deaths per year in lakhs. To improve living conditions and the introduction of antibiotics can result in drastic reduction of this typhoid fever morbidity and mortality. But still, in developing areas of Africa, America, Southeast Asia, and Western Pacific regions, this disease continues to be a public health problem. Even we face a lot of issues in our institution also sometimes during rainy seasons. So this typhoid risk is very high in populations with they lack access to safe water and adequate sanitation.